Welcome, Sylvain. I'm very happy that you will be talking about your open hardware ISO7816 smart card interface FPGA software.
I will quickly present the work I've been doing on the FPGA core for smart card interface. I'll start with a quick intro of what is ISO7816 and kind of a couple of specific points that are relevant to this talk. Then the FPGA core itself and the test setup I've been working on so far. So what's ISO7816, or more specifically the -3 version? It defines the electrical interface and transmission protocols that's used by all smart cards with contacts. So physical contacts, not wireless or anything. It's actually quite broad in the sense that it covers things like signals level and higher level protocol and that kind of stuff. Here we won't really focus on that. We will only care about how bytes are exchanged at the lowest level, because that's really all that's relevant to the FPGA core itself. Anything the low level electrical details, we're going to assume that's taken care of by an external chip. Because if you want to be compliant to the specification, you need to, handle 1.8 volt, 3.3 volt, 5 volt interface, that kind of stuff. That's outside the scope of the FPGA core. And anything higher level, like the T1 block or the APDU or decoding the ATR, all those higher level of the stack, which are also specified in the document, they will be taken care of by software. You're not going to implement that in gateway, in logic, in the FPGA. So basically, the only thing we're going to care about is the I/O line, which is the bidirectional line through which all data are transferred. So the way bytes are exchanged to a smart card and from a smart card, it's basically a UART, except it's bidirectional. We're using only one line. And it's 8E2, meaning 8 data bits, even parity, and 2 stop bits, with just a couple of tweaks to that. The first one is probably the most special one, is the per character error reporting and retry mechanism. And if I think I have, yeah. If we look at so that's from the spec directly, and that's how bytes are exchanged. You can see so you start a UART with a start bit, and then the 8 data bits, then the parity bits, and here the receiver will actually check the parity, and if it's incorrect, the transmitter will release the line, which will just be pulled up, but through a high impedance resistor or something like that. And the receiver can then, if the parity was incorrect, assert and bring down the line to signal the error. The transmitter will then sample this, see that there was indeed an error, and retransmit the same byte again, so that the transmission can be error-free, basically. That's one of the main specificity. The other things is, in theory, you have 2 stop bits. That's kind of the default and the minimum. But a card can actually specify that it wants more than that. And so the actual gap between 2 characters, which in theory is just 2-bit time, can actually be extended further than that, if need be. There is also the concept of a max wait time. And that's basically the maximum time between 2 characters that the receiver will wait. So if the receiver is waiting for data, there's actually a timeout that's specified, and the card has to answer within that time. And if it can't provide an answer fast enough, it can actually transmit a special character to ask for more time, basically. But that allows to check that the communication isn't dead and that somehow we didn't get a deadlock or something like that. And if that happens, then, well, you basically just reset and start over. The other kind of special thing is that in a normal UART, you just specify a baud rate like 115 200 or something, or 9600, and this is kind of an absolute value. Here, the speed of transmission is always derived from the card clock. So each card has a clock input, which can be fed by basically any frequency within some bounds. Like you have a maximum, of course, and the baud rate will be derived from that clock. If we look, it's actually defined as 1 bit time, which is called a 1 ETU in the spec, is F over D multiplied by 1 over the inverse of the frequency. So basically, the higher D is, the higher the baud rate is, and the higher F is, the lower it is. And you have tables in the specification that tell you what rates are supported by the card, and there's a specified procedure to change the speed. Like when you boot the card at first, it will come up at some default speed, and then you can go through what's called the PPS procedure to change to a higher baud rate within what the card declared that it can accept. Now, it's important to note that even if the frequency is derived from that clock, all communication is still asynchronous. So this is just basically purely used as a frequency reference, as a speed reference, but like there is no phase relationship. Like the signals here won't transition exactly on the clock boundary or anything like that. It's still asynchronous communication. Now the specification also includes things like when the signal must be sampled and when transition are allowed. That's what essentially this diagram shows, is that the transmitter, each interval is 1 bit time, right? And starting from the first time that the data is, that the start bit is asserted, every other transition has to be within plus or minus 0.2 ETU, and that's the ETU being the bit time. That basically dictates the maximum jitter that you have and the maximum frequency error that you can have over the entire transmission of the byte. And similarly, the receiver has specification as to, okay, from the first time it detects a low state, which is the beginning of the start bit, it needs to sample at exact, this will be defined as instance 0 or moment 0, as it's called in the spec. And it needs to sample the data on the line at 0.5 plus or minus 0.1 ETU, or 1.5 plus or minus 0.1 ETU. And that's what the specification tells you when you're supposed to sample the signal, basically. So why would you want an FPGA core for ISO7816? Because after all, there are several microcontrollers that can implement ISO7816. Like we used one in the SimTrace, actually 2 different ones. And I mean, SimTrace works, obviously, so it's possible to do it. And there are plenty of other microcontrollers that support it. However, I've heard some rumors that some of these cores, even some we can coerce to work in ISO7816 mode, but it's not ideal. Some others, they actually have an ISO7816 mode, but it can be quirky to use with some special cases of stuff like that. I have no personal experience with them, so I can't really comment. Secondly, your selection of microcontroller becomes a lot more restricted if you want a lot of those UARTs. Okay, like if you want 1, that's fine. If you want 8, that becomes more of a problem. If you want to implement like a massive SIM bank and have a 32 SIM at the same time, I mean, good luck finding a microcontroller that will have 32 UART blocks. But in an FPGA, I mean, you can fit, as long as you have 32 I/O lines, basically, you finding a a smaller CP5 that will fit 32 UART core shouldn't be much of an issue. And of course, the other problem is that even if those UC exist in theory, doesn't mean you can actually buy them because 2021. So the other reason you might want an FPGA core is the flexibility. Those cores might be designed to be able to talk to a smart card, but maybe they can't actually act as a smart card because they can't take the external clock as a reference. Or maybe they're not ideal for sniffing, because if you're sniffing, you might want to receive, be aware of the retry mechanism, but not actually drive the retry line, because I mean you're supposed to be passive. You can't assert the error line yourself. You have to just note what's happening and still discard that bit, but you can't be driving the line. Or if I use other weird things that I can't think about right now, but in the past, it's not unheard of for Osmocom to do weird things and have weird requirements. And so an FPGA core, if it implements the spec, you can always tweak it to do whatever you need it to do, whatever that is. And the other reason, of course, is that I just like FPGA, so why not? So when what were the objectives when I started to design that core? Well, the first one was obviously to be compliant to the standard to a reasonable extent, I would say. And so I've tried to stick to when to sample the signal and how to output to respect the timing as much as I could, even in some of the extreme cases. The other design goal was to be small enough to fit in relatively small FPGA. The target would be something like a UP5K or possibly a small ECP5. We're not going to use like a Kintex UltraScale to implement UART. That doesn't make sense. That implies first, well, designing the core correctly, obviously, and finding kind of the right balance between what features you're going to implement in hardware, hard logic. For instance, like the retry mechanism, you have to implement it in hardware because it's very timing critical. There is absolutely no way to implement that properly through kind of software emulation. That's just not going to happen. The wait timer, that's something that's reasonable, at least partially can be implemented in software. Like you don't have to generate the timeout. You just need the core user to be able to notice that there will be a timeout, at some point, or things like that. But you don't need it to implement the actual transmission of the wait character or that kind of stuff. And of course, since the flexibility was a big reason to go for an FPGA in the first place, the core has to have an architecture that's flexible enough so that any kind of small modification that you may need to have to the behavior, you can actually do it. The primary application has been written for is to talk to a smart card, but I've tried to keep in mind kind of the specificities that would be needed if we wanted to implement a passive tap or man in the middle or actually act as a smart card. I mean, acting as a smart card is actually pretty similar. There's not much difference, but so that's basically what I had in mind when I started to implement it. Okay, I've noticed that this slide is cut off, but okay. I've divided it in 4 blocks. 3 of them are implemented, 1 is not, because it's not actually needed now. So I kind of left it as a future task. And for UART, like one of the primary things you need to do is generate the timing. When do you want to sample bits and when do you want to output them? Now, because the because the baud rate is directly related to the card clock, whatever that is, there is two big cases that present themselves. The first one is the synchronous and the asynchronous. And what I mean by that is that the synchronous case is where the ISO7816 logic inside the FPGA is clocked by the same clock as the card clock or a multiple thereof. Like, for instance, if the FPGA internal logic is clocked at 20 megahertz and it provides 5 megahertz to the card, but that 5 megahertz is a divided version of the 20 megahertz provided to the card. That's fine. That's what I call synchronous. They're derived from a single clock source, basically. That's the first case. And the other is well, they're not. That would, for instance, happen if you wanted to act as the smart card, and so the clock is actually an input to the FPGA, and maybe the SoC in the FPGA that's driving the core is actually clocked by a 48 megahertz crystal for USB, and then the incoming clock of the smart card that you get is completely unrelated to your internal SoC clock. But yet you will need to derive baud rate that's actually related to that clock, whatever that is. So you will need some way to measure it and generate the appropriate timing. That will probably take the form of some digital PLL, basically dividing the incoming clock, sampling it in your core clock and that kind of stuff. But as I said, that's remains to be implemented because that wasn't strictly required now. Now, even in the synchronous case, which is arguably the simpler case, there are still a couple of tricky things to handle. The first thing is that if we go back actually to the formula here, you have one ETU is F over D. So, F, the big F settings parameter, I would say, is easy to handle because you just take your main clock, your system clock, and you divide it by F. That's super easy to do in FPGA. Now, multiplying it by D, on the other hand, that gets more complicated. Now, if the ratio simplifies, obviously that's like super easy. Like, for instance, if you have a 2048 and 16, one is divided by the other, that doesn't matter. But you could very well have, I don't know, like DEI is 64 and FI is 372, and they're not. You can't simplify that. At least I don't think you can. Yeah. And so the way it's implemented in the FPGA core here is through a phase accumulator, where you have a counter that you load it initially with the F value, and you decrement it every clock cycle by the D value. When that counter goes negative, you know that you need to generate a tick. Like that's when you need to send a bit, for instance, and you re-add that the F value to the counter, keeping whatever underflow you had. And so this will basically generate a tick rate that's approximately the right baud rate, plus or minus one clock cycle. You have some small jitter because you have to generate things aligned to your system clock, and the baud rate that you might be asking might not be an exact divider, so you can't be more precise than that, but that's the best you can do, basically. The other kind of tricky thing is caused by I/O delays. So the BRG block will actually generate not one single strobe, but two strobes which are slightly offset from each other. The first one, okay, they're kind of badly named. They're named Tix and Eric's, but that has nothing to do with the UART transmit and receive. It's more related to transmit and receive from the I/O. And that's because your core logic will execute, okay? But whatever signal it sees at its input from the outside is slightly delayed in time. Like it sees the signal that were outside slightly late because, for instance, at the input, at the minimum, you would have an FF synchronizer, which is a 2 clock delay, 2 clock cycle delays to avoid metastability and things like that. But you might actually have a deglitch filter, which will delay the signal even more to avoid like noise on the line and things like that. And then you also have some delay in the other direction, in the sense that when your core instructs the IO to drive something, well, you might have IO register that will add 1 clock cycle delay. So you might think that, in this case, we would have a round trip time, basically, a minimum of 3 cycles. You might think that's not very significant because it's only 3 clock cycles, and the card clock might be 5 megahertz, and the baud rate might be 9,000 baud or something. And in a lot of cases that's true. In a lot of cases that very small delay doesn't matter. However, if we look back at the table here, you can actually get in some cases where if you have very high value of DI and very low value of FI, you can actually have pretty high bit rates compared to your system clock, where you only have like something like 10 or 15 system clock cycles per bit. And in that case, if you have only 15 clock cycles per bit, if you have a misalignment of 3 clock cycles, it's very easy to screw up here and not sample within the plus or minus 0.1 ETU interval that you're supposed to sample into, for instance. So that's kind of the specificity of the bitrate generator. And the other thing it does, obviously, is generate those pulse properly aligned, so that you see here it has a sync input, which is used when receiving. At the beginning of the byte, it will synchronize so that the first pulse that's generated is right at the 0.5 ETU mark to sample in the middle of the bit. And that will be resynchronized at every byte, basically. So that was primarily the way the BRG works. It's not very complicated. I've decided to implement it that way rather than some other, like if you look at in microcontrollers, sometimes you will see that they generate actually like an 8 times clock something, and then they sample the data 8 times and try to find the best alignment. But that was actually pretty hard to make it work, to make something like that in and still obey like the specification, and to make it work for cases where you have high baud rate compared to your system clock rate. So that's why I went with this route, basically. The other block is the ISO7816 core, which is really it's basically a shift register, and it handles the retry and gap handling. I mean, you can have a quick look at what it does. So really, it's the low-level byte interface where whenever it's received, well, obviously you have the I/O interface to the FPGA I/O pad, so like input, output, and output enable, right? You have the transmit interface where you basically tell him, okay, I want to transmit a byte, and at the end it will tell you, okay, how did that work? Basically, it went okay, or did it went okay, but it was retried, or it failed, because this core implements retry, but with a limit. Like it won't retry indefinitely. You have a configurable number of retries, and so the transmit might eventually fail. At that point, really, the only thing you can do is reset the card, because there's nothing else to do. And you have the receive interface, which again, whenever a byte is received, the core will tell you, okay, we've just received the byte, but it was retried, and it will only tell you the value once, or this was a parity error or frame error. Frame error being either the stop bit was not detected properly, basically, which means that it was just losing the line. It's just the interface to the baud rate generator, because you want to be able to use the core either with the synchronous or asynchronous one. So this is split off. And the rest is just configuration registers. Basically, they're constant. Like the core can't work if you change these in the middle. And that's just, do you want to enable ticks? Do you want to enable RX? And things like the extra guard times and above try, and if the retry mechanism is activated or not, because it's actually optional. Like if you work in T=1 mode, I think you don't actually have that mechanism. So you have to be able to act as a normal UART as well. Something actually to note about this is that this will not receive its own transmission, because it only has internally it only has one shift register, so the hardware can't even work in both RX and TX at the same time, meaning that it TX has priority, basically. If TX is enabled and there is a byte to be transmitted, it will transmit it, and that will automatically disable the receive circuitry without the user having to do anything. So that because I didn't see any point in ever receiving your own bytes. I didn't think that was really useful. So yeah. And the third block is this interface is nice and all, but it's not really what you want to drive from a SoC, right? Because it's kind of still very low level. And so you have ISO7816 WB, which is basically a wishbone wrapper. And this will contain basically all the configuration register and FIFOs. The FIFOs I've used here are actually, I've kind of sized them for the UP5K. We might actually make them configurable because in some other FPGA, it might make sense to have them smaller. They're actually large enough to contain the maximum sized APDU, meaning that the user can really just dump the entire APDU in the FIFO without having to worry about the FIFO filling up or anything. And same thing, it can actually wait for the entire answer from the card before even having to check if there is any character, because if the FIFO is empty at the beginning, there is no way the card can fill up the entire FIFO. So it can just wait for the entire APDU to be received and then read it all at once. There is actually documentation about on the register map. What kind of register that offers, and it's very classic. You have like a control static register, which you will basically be checking pretty often. Which okay, this is obviously wrong. That would be 0, I guess. Yeah, I have just changed some of the mapping of the registers. So obviously, I have yet to update the documentation completely, but that's the general idea. We just basically, control the RX, if you want to enable it, and different status bits, like if the FIFO is full, empty, or that kind of stuff. Then you have the data register, which is access to the FIFO. If you read from that register, it will read from the FIFO. If you write to that register, it will write into the FIFO. And then you have a bunch of configuration for different things, like the extra guard time, as I mentioned. You, in addition to the 2 pose bits, you need to be able to put more than that in between 2 bytes, so you can configure that, the number of retries you want to retry, and then okay, when do you want interrupt, if you even want interrupt at all, or if you want to use polling, you can use polling as well. And then the wait timer. And the wait timer is actually a bit sort of noteworthy because it's actually rather large. Like if you look in the spec, the minimum and the maximum value for that wait timer is a very large range, and so it turns out that the implementation of the wait timer is actually a significant part of the core itself, just because of the number of bits that it takes to count that high. But I'll show that later. And then the configuration of the board rate generator. It takes the F and D values that are configured from the card PPS directly. So those F and D value, you can just basically put them directly into the configuration register. With one minor tweak is that if the system frequency is not the card clock frequency, you actually need to factor that into the F value. But that's actually documented. Like it tells you, okay, yeah, you need to fill the register with that values. The BRG phase, that's a bit. It's one of those compromise between the ease of hardware and the ease of software, because implementing this in hardware would have been possible, but it would have been rather. Sorry, I've just noticed that the chat wasn't scrolling down automatically, so I was missing the messages. I will address those in a second. Sorry, what was? Yeah, the phase register is a compromise between what you do in hardware and what you do in software. It's basically the value that you need when you receive to align your first receive pulse from the BRG so that it falls right into the 0.5 range that you have here. And it's not complicated to compute, but doing it in hardware would be basically costing hardware for no good reason, because it's done once at the initialization time. And so the software can easily calculate that value rather than wasting a bunch of hardware doing a bunch of multiplication inside the FPGA for no good reason. So addressing the chat notes, yes, indeed, it's 3 volt, not 3.3 volt when talking to the card. Yeah, that's kind of speed. So Orkan mentions like 200 kilobaud with a card clock of 3.22 megahertz. That's definitely not a lot of clock. That's something like 5. So yeah, like 15, 16 system clock cycles per board, and so that's definitely not trivial to place the sampling pulse. Where is it? To place the sampling pulse and the transition right into that 0.2 ETU window. Yeah, I'll talk about the footprint right now. And yeah, the way I handled oversampling here is basically, instead of doing, it's an option. Like if you don't, so oversampling is meant to prevent glitches. Basically, like you don't want to have like if you sample a rogue 0, you don't want that to trigger suddenly the receive or that kind of stuff. The way I would handle it here is basically here, instead of the synchronizer, you can replace this with another block, which is a glitch filter, which will basically prevent transition. It will require a certain number of clock cycles of the same values before transitioning. It's basically sort of a digital hysteresis. And that's the way I handle glitch filtering. So it's not, I mean, it is oversampling, because basically we are oversampling, except instead of being 16 times the baud rate, we just oversample at the system clock frequency all the time, which, might be 15, 16, or if your baud rate is low, it might be oversampling by a factor of 1,000. It's just, kind of a fixed frequency sampling. But as I said, this introduces a delay, and so you need to increment this, and that works up to a point. When you get to some of the higher baud rate at lower clock, if you are the master, the clock master, that's still something you can deal with. But if you are a card or trying to emulate a card, that gets a little more tricky. And some of those cases, I'm not sure we'd be able to handle them. At least with this core, I need some tweaks. So here's the results. It's actually a bit bigger than I would have hoped. Unfortunately, I'm sure there are still ways to reduce it. I haven't really dug into. So it takes about 430 LCs with the wait timer and 320 without the wait timer. That's why I was noting the wait timer, is because, as you can see, it's like nearly just that one timer is 1/4 of the size of the core, which is definitely not small, right? And so if you're only planning on using one or two of those cores, it makes sense to include the wait timer because the cost isn't that high, and it's very convenient because you need to implement a timer one way, right? So the two ways to do it is either with the dedicated wait timer, which is clocked here by the core itself at the right baud rate or something like that. The other option is to emulate it, basically using a standard CPU timer, like the RISC-V, standard 64-bit timer or something, and just handle it in software, computing whatever time you need to wait yourself. And so for a single or two UART, you can include it. It doesn't cost much, and you would have to pay the price of a normal software timer anyway. However, if you're thinking about 8, 16 or more UART cores in a single FPGA, maybe it's actually more efficient to start thinking, okay, I'm just gonna handle the wait timer entirely in software using a unified system timer, and just interrupt at the right time and compute whatever is the next expiration and stuff like that, rather than rely on dedicated hardware. So yeah, a bit of a compromise. So that's the test setup I've been using so far. So it's Icebreaker board, which is like my go-to UP5K development board. It's really just directly connected to the IOs. And then a board that's been provided by Harald, an NCN8025 breakout. So the NCN8025 basically is going to handle all the electrical aspects that I was mentioning. So it has level shifter, it has internal regulator to provide power to the card. It has internal clock division circuitry, so that I always send it 20 megahertz, and I can select if I want to send the card 20 megahertz, 10 megahertz, 5 megahertz, or I think even 2.5 megahertz if I want to. I think it goes up to 128. And the architecture of the test sock is, very standard, I would say, for what I usually do, is that I have a Pi-Core V32 RISC-V CPU. I might actually change that to a VEX RISC-V because the VEX is actually smaller and faster in the sense that it can retire more instruction per clock cycles. The downside is its maximum frequency is lower, but here it doesn't matter because this entire thing runs at 20 megahertz. And so the VEX can be clocked at 20 megahertz. There is no problem there. This is connected to a 1 kilobyte boot ROM, which is what the FPGA boots from, and 64 kilobytes of RAM. The RAM is internal to the FPGA, but if you don't know, in the UP5K, you have those large single port RAMs, which are nice because they're large. The downside is you can't initialize them. So that's why the content is random at boot. That's why I have a small boot ROM, which is implemented in small block RAM, which those you can initialize. And this code will just go through the SPI controller, fetch the program code and data from Flash, load up the SP RAM, and then jump to it. The other peripheral, GB LED, a debug UART, so I can have some bidirectional communication. Standard GPIO block with input, output, and direction setting. And this controls pretty much all the bits here of the NCN8025 breakout, except for the I/O line. And the I/O line is connected to the ISO7816 core directly, basically. So that's actually what I have running here. Okay, but we can actually have a quick look at the code first, maybe. So I've only done very basic testing at the moment. And that's basically the sequence that I'm executing, is that I do some setup of the core, which configures it, for basically the default parameters that the card will have at boot when it gets out of reset, which is like the standard F and D values, along with the mode and the move retries, that kind of stuff. I should document these, but yeah. This basically clears the various status flag of the FIFO and stuff like that. And then it executes the power-up sequence of the card, which is specified in the NCN8025 datasheet. And then finally, it will read the ATR, which is the answer to reset from the smart card, which is the first thing that the smart card sends after it gets out of reset. It will send a PPS request asking the card to change to a higher speed. And then it sends a test APDU. Honestly, I have no idea what that APDU is. I can't even remember where I got it or what it does. But it's a valid APDU that the card will answer to. And as you see, I don't even bother checking if the FIFO is full or not, because I know it's not going to be. Like the FIFO is large enough to contain an entire APDU, so I don't need to bother with that. Wait some time for the answer, and then read the data value, basically. And so I can execute that on the card. And yeah, you see basically the answer to reset from the card, the PPS response, which is basically what I've sent, which means that the PPS was actually a success. And then sometimes later, the card actually answers. And I think, yeah, that's the code for OK. So obviously communication went fine. C0 is get response. OK. I have no idea what's C0. But I didn't ask any questions. So what is what is it the response to? It's a good question.
Yeah,
Maybe whatever is
idea.
left in the buffer. Anyway, yeah, I knew it was just providing some valid data, but yeah, at least some data. I'm not sure if it's valid or not, but something. So that's basically the testing I've done so far. So what needs to be done yet? Well, more testing, obviously, because I didn't want to implement a full ISO7816 stack because there's already one written, and so it needs to be like see exactly what the best integration would be of that core into the existing firmware is. Optimize size further. My expectation is that, I mean, Yosys always screws up something. Like there's always something that could be done better, and that might be able to shave off a bit more. Because at kind of what I wanted, like the original goal was to try and fit 8 of those UARTs. The RISC-V core and a USB core inside the FPGA. And I think that's doable at the moment. With the current size, it's doable if you don't include the wait timer. But just about, and I think there's still like some places where you can probably shave off a few registers. And the thing is, when you multiply, when you have one core, that 10 LC doesn't matter much. But when you start multiplying it by 8, that tends to grow very quickly, especially in a UP5K. Like I didn't give any numbers. I mean, I gave numbers what the size it takes in LCs, but I didn't, like the UP5K. The 5K is basically the number of cells, so it has 5,000 LCs, right? So 430 LC is basically slightly less than 10% of the FPGA, maybe like 8% of the FPGA, something like that. Obviously, the UP5K is a very small one. On something like a smaller, even the smallest TCP5, it would be less of an issue. And if you go to the larger size, then writing the actual asynchronous baud rate generator. As I said, the only thing I have some draft on paper on how it would work, and that it should be possible to have it actually meet the spec and generate valid signals, but I haven't actually written it or tested it in any case. Check with other modes to make sure that the core does everything it needs to. I think for card mode, there's really not much that would be different, as far as I know. For stiffer mode, as I said, something it doesn't do at the moment is that we need a way to enable the fact that the core is aware that there's a retry mechanism, but it ignores the retry value. That's something that's currently not configurable, and that needs to be added, but that shouldn't be very complicated. Then finally, actually use the core somewhere, because at the moment it's just written, but it's not being used for any real application yet. So of course I'd like to thank Sysmocom and Harald, because they've commissioned this work and sponsored it, and provided the hardware, both the breakout and the smart card that I've used for the testing. So that was definitely a fun project. And yeah, some further reading, and I would put a link to the specification, but unfortunately you have to pay for it. So there you go. Thanks for your attention, and if you have any question, can answer them, maybe.
My first question would be, why exactly is that wait timer so large? Is it just because the counter value has so many bits? I mean, and if so, why can we not just divide the clock first and then, or does it not make a difference? I mean, the divider also uses the same number of gates. So.
Yeah, I mean, it's so the main reason is that the value of that, if you look at the spec between the difference between the minimum value that wait timer has, which sort of dictates how much you can pre-divide, right? Because you need to be able to set a value that's like half of the weight, so that if it's very short, you need to be able to set it to a very short value. And the maximum value that it can have is very large, and so it needs a long number of bits, which implies that you need a fairly large resistor, like I think it's 24 bits, to store the configured value, and then you need another register to store to actually count, and then you have some logic that can't be optimized out. It's definitely bigger than I expect. I can't remember. I think a part of it is that Yosis is doing something wrong, but I can't. I couldn't, because like in my head it shouldn't be, because I measured it at more than 100 LCs, and in my head it should be something like maybe 60 LC or something. So there's definitely something that's going wrong somewhere. But I haven't been able to trace it, and it goes very with those large registers, as soon as instead of using, 1 LC per bit, if the synthesizer doesn't optimize something and start using 2, well, you instantly have 25 more LC, and that tends to grow quickly. So that's one of the reasons. One possible way out of it on the UP5K, that's something I've thought about, I haven't implemented, but that would be doable, is that the UP5K actually has DSP blocks, which are completely useless in this application. We don't need to compute multiply and things like that. But those DSP hardware blocks inside the fabric, there's 8 of them. And the nice thing is that they include some 32-bit wide registers and 32-bit wide adders. And so you could actually implement both the configuration register to store whatever timeout value is and the actual counter to compare to that value inside those DSP blocks to basically implement the wait timer at a much lower cost in terms of logic. So far I haven't actually done that because this would be purely ISO40 specific, while the rest of the core at the moment is portable to any architecture without modifications.
Yeah, thanks for the explanation. I mean, my stupid idea would be then to have something like a configurable divider and a shorter length shift register, but I'm not sure if that, as you know, I have no clue about FPGA development. So.
Yeah, but that's the thing, is like the configurable divider is probably gonna take the same amount, like the configuration register for the divider plus the divider itself is probably gonna take the same amount of logic as just having the full number of bits in the wait timer, basically. That's sort of how it works.
Okay, never mind.
In practice, what is the this wait timer used, and is it really critical that it's so configurable, or is this just to check that the thing isn't dead?
Honestly, I'm not entirely sure I'm the best person to answer that question, because the spec, the spec just says, okay, like after you have a maximum time between those bytes, and you need to use that timer. I have no idea in practice how that's used, or that's Harald or Orkan probably best to answer.
Well, the point is, this is particularly important if you are doing card emulation, where basically you have this wait timer, which is also negotiated as part of the PPS, as far as I recall. So it's basically dynamic how long that actually is. And if you're emulating a card, particularly in a remote emulation or something like that, you may not have the response to the command that the reader is asking you before that waiting time expires. So you need to sufficiently before that timer expires ask for this waiting time extension, and that's how we do it in SimTrace card emulation. For example, we have a hardware timer counter block peripheral in the SAM3S, or now I think it's even done with a counter that is inside the UART, so that when half the waiting time is expired, we send a waiting time extension byte to the reader to make sure we get some more time while we wait for the USB host and whatever may be behind the USB host to send us the response to the command the reader has sent. But certainly for this application, the accuracy could be significantly reduced. We just need to know reasonably well in advance to send that extension, or one could probably even, well, but then you still need a counter if you do it completely inside the FPGA. I'm just thinking you could even automatically send that waiting time extension and not have a timer to report back to the software that something needs to be done. But then still, you need to count somehow the time that has expired.